This week, our topic is going to be weather and climate. So it's probably a good idea to start with a few definitions. The atmosphere, that's the layer, I could have put that on here, layer of gases that envelop the Earth. And the atmosphere really is very, very closely tied, as we'll see, with the hydrosphere, or the water that's present on the surface of the Earth. Weather is the state of the atmosphere at a particular place in time, and the climate is the long-term average weather for a given area. So the two are related but should not be confused. So weather is what's happening today, and climate allows us to compare today's weather to the weather that we experience over the course of the year and from one year to the next. And it also allows us to compare the weather patterns that we experience with the weather patterns that are experienced in other places. Wind is just the mass movement of air, and humidity, and I'll have another slide with more on humidity, but humidity is the percent of the water vapor in the air compared to the amount of water vapor that the air could hold. And really the correct term for that is the relative humidity. So let's start by taking a quick look at the composition of the atmosphere. When you take a deep breath, you are mostly breathing in nitrogen. 78% of the atmosphere is nitrogen. 21% is oxygen, very important. The number 3 gas is argon. And then you'll notice water is kind of different. While the first 3 are fairly evenly mixed and don't change relative to each other or overall much at all, water goes up and down by quite a bit. So if you're in a very dry area, you can have as much as very, very close to 0% water in the air. And in some places, it's as high as 4% of the air is water. And that's in vapor form that we're talking about. Carbon dioxide, which we'll talk about a little bit more toward the end of all these slides, is another important component because it helps the atmosphere retain heat. It is our most significant greenhouse gas. As of January 2021, so as of about a month ago, the level of carbon dioxide in the atmosphere is 415 parts per million. And there's a graph over here to put this into context. The highest previous concentration over the last almost million years is about 300 parts per million. And we've seen the percent carbon dioxide, or the parts per million of carbon dioxide in the atmosphere, has been going up very, very, very steadily for the last really couple hundred years. So, and we can look at a chart of that increase later, but I'll just give you a quick preview. This is one of the last slides we'll look at, and that's in terms of the role of each of these greenhouse gases in retaining heat. And you'll notice the carbon dioxide is number 1. So anyway, in your book, I think it gives the parts per million is 380. That's a couple years ago. So that just shows you how quickly this is rising. All right, so relative humidity. Here's the slide I promised. It is the percent water vapor in the air compared to the amount of water vapor the air could hold. It varies with temperature and air pressure. And what we will see is there's a complex relationship here. Generally speaking, as the temperature goes up, you can put more water vapor in the air, and as the temperature goes down, water vapor will come out of the air and turn into little drops of water or little ice crystals. However, as you might remember from a couple weeks ago, when water changes state, it absorbs and releases heat. And so that makes this relationship more complex. And we'll see some of the effect of air pressure in a few slides. 100% relative humidity results in the formation of water droplets or ice crystals, as I just mentioned. And again, that is going to absorb or release heat energy, depending on which way we're going. The dew point is the temperature at which the relative humidity will equal 100%. So if the temperature outside is dropping, when it gets to the dew point, usually the temperature stops dropping and water droplets or ice crystals will form. So we'll get fog. And I'm looking outside my window right now, and we've had fog off and on for the last day or two, just because we've got a lot of snow on the ground, so that cools the air off. But as that snow is melting, that water vapor is going into the air. And so as the temperature kind of bumps up and down a little bit over the course of the day, that water vapor may come out as water droplets and create some fog. A little bit on density. The density of the air increases with a decrease in temperature and with an increase in water content. So if you make it cooler or you add a lot of water, that will increase the density of the air. And the air is going to rise and sink based on density. Warm air, generally speaking, rises. Cool air, generally speaking, sinks. But as we mentioned, water plays a role in this as well. So there's a very complicated relationship between the density of the air pressure, the temperature, and the water content. They have this figure in the book that shows you one general rule that we follow, which is as air rises, it expands and cools. When air sinks, it compresses and warms. And one of the things that will happen as air rises, because it expands and cools, it actually has the ability to hold less water. And so at a certain combination of pressure and temperature, water droplets will begin to form and we will see clouds. And if you ever look up in the sky, you'll notice that the base of the clouds is usually relatively flat because that represents the point in the atmosphere where the pressure and temperature are such that water droplets are likely to form for the moisture content in the air at that location. So again, kind of complicated relationship, but we have some general rules that we follow. So when air rises, we will generally see clouds form, and if air is sinking, we will see instead the air will tend to get warmer and pick up moisture. And so when the air is sinking, you basically have clear skies and it's dry. When the air is rising, you typically have cloudy skies and often get rain as well. So let's look at the Earth's heat budget. So we want to talk about energy. First of all, it's important to know these big arrows at the top. 100% in, 100% out. Everything that comes in goes out. If it didn't, the temperature would start to increase, which tells you a little bit about what's going on with global warming. The air that comes in is light energy, and light is high quality energy. It's very concentrated, it's very good stuff. So what happens when it hits the atmosphere? Well, you'll notice here, some of it is absorbed by water vapor, dust, and carbon dioxide. Some of it is absorbed by the clouds. And the big number here is 51%. A little more than half is absorbed by land and water. You'll also notice that about 30% gets backscattered or reflected before it can basically warm us up or do anything for us. So we just send about 30%, almost a third of that incoming energy right back out into space without doing anything. Now, the really important part are the parts that are absorbed, and especially important is this 51% that's absorbed by water and land. We go over to the right side of the diagram and we will see that that 51% is released back into the atmosphere as long wave radiation, which is heat energy. So when the ground gets hit by the sun, the temperature, it absorbs that energy, the temperature goes up. And you know, if you put your hand down near the ground on a sunny day, it'll feel a little bit warmer. You can really feel this effect over stone or concrete, or when you're on the beach. Now, latent heat is the other one I want to spend a little bit of time on, which is that is the water vapor going into the atmosphere. And when water absorbs energy, it can turn into vapor. and you might remember from a previous set of slides, the water can absorb a lot of energy when it turns into vapor. It then carries that energy up into the atmosphere, and when a cloud forms, that energy is released because the cloud is made of droplets of water or little ice crystals. And so that's what's going on here. You'll notice that the big way that we warm up the planet, 51% here, is energy absorbed by water and land and then released back into the atmosphere through these other mechanisms. Now you'll notice ultimately that energy goes back out into space as infrared long wavelength energy, which you would experience as heat. That's considered by physicists to be low quality energy because it's long wave. It is less concentrated, but it all ultimately goes back into space. The key to keeping us warm is this part right here in the atmosphere. Things like water vapor and carbon dioxide will hang on to that energy in the atmosphere for a little bit and then release it back into space. And that's what keeps us warm. This is similar to what happens when you put a blanket on your bed. It helps keep your body heat in for a little while, and then it's released back out into the room. If that blanket on your bed kept all of the heat in, you would very quickly get too hot and throw the blanket off. So the atmosphere holds that energy for a while, and then it goes back into space. Now, this energy delivery is uneven. So if we look at where the sun's rays hit, if you're in the upper latitudes, as you get closer to the poles, you'll notice that the rays strike the surface at a lower angle. If you're near the equator, the light rays are coming straight on. Now, what impact does this have? Well, if the light is coming in at a low angle, it becomes more spread out. You'll notice if the angle is 30 degrees, that light is spread over 2 unit areas, or essentially twice as much area as if the light is coming straight down. So the equator is getting this light energy. It's more focused, and as you move farther and farther north or south, as you get closer to the poles, that same amount of energy is spread out. In addition to that being spread out, because it's coming in a lower angle, it has to go through more atmosphere to get to the surface of the Earth. Think about what the sun looks like at sunset. You see that red ball instead of the bright ball. And the reason you see that is because the light has to pass through more atmosphere, and the atmosphere scatters and absorbs that energy before it can get to the surface of the Earth. Number 3 on this list, when you're at the higher latitudes, you get more reflection. That light is coming in at a low angle. It's much easier for it to bounce back out into space. The end result is that if you are close to the equator, near 0 latitude, you get extra energy coming in compared to what goes back into space. What goes back into space is the blue line. What you're receiving is the red line. As you get closer to the poles, as you go into the higher latitudes, you can see we get less energy coming in and more going out, and so there's a deficit which would tend to cool those areas off. Now, the Earth and physics are going to try to remedy this by circulating the air. And the process for this is what we call convection. Warm air rises. It then moves to a place where it gives off its energy. As it cools off, it becomes more dense and it sinks. And then it goes back to the warm area. And so this circulation evens out that energy deficit. What that means is the heat transfer here that you see is going to take place in the atmosphere, and we'll find out, I think next week after the exam, we'll see how ocean currents fulfill a similar role. What we're going to do on the next set of slides is look at some complications in this initially simple process.